Welcome to Calculus. Today we will find volume by cross-sections using triangles and semicircles as our cross-sections. We'll take a look at two examples. Our first example has as its base of the solid the region enclosed by the semicircle, which is pictured here. So it's defined by the equation y equals the square root of 25 minus x squared and the x-axis. Our cross-sections are perpendicular to the x-axis. So I'll begin drawing a few of these cross-sections perpendicular to the x-axis. And what these are isosceles right triangles. And the pieces that I'm drawing right now are one leg of those, each of those isosceles slices in the XY plane. So I'm just going to try to draw this somewhat three-dimensionally just to show that these are right triangles. They're isosceles, which means the legs are congruent with each other. And that's going to generate for us our solid. So let's start by setting up our integral. And what I'm keeping in mind is that I'm really using the area of these isosceles right triangles. So if I were to bring one of them just to take a look at it on the sideways, it would look something like this, where my two legs are congruent. That's not to scale, but they are congruent. Which means for us, when we're going to find the area of each of these cross sections, it's going to be 1/2 times the base times the height. But since the base and the height are the same, we can think of this as 1/2 times base squared. And the way that we're going to define the base is according to this semicircle. So that's going to be defined by the square root of 25 minus x squared. So we'll set up for volume here. We're looking for the volume of the solid. And that's going to equal for us the integration from left to right. So I'm integrating with the limits of integration from -5 to 5. And it's going to be 1/2 base squared. So the base, of course, is the square root of 25 minus x squared. If I wanted to, I could say -0 to represent the x-axis. Since we are integrating from left to right, our functions need to be the upper one minus the lower one. And then according to my area formula for the right triangle, that's base squared. And then I'll put dx. So that sets up the integral. At that point, we just want to evaluate. So I'm going to bring it that 1/2 out, let it pass through the integration. And we'll simplify the integrand here. I basically have square root of 25 minus x squared, let the 0 go, squared. So that's going to collapse the radical. So all we got left is 25 minus x squared dx. So that's ready to integrate. So we'll do so. This is going to be equal to 1/2 times bracket and then 25x, that's integration of 25, minus 1/3 x cubed. And we'll evaluate from 5 down to -5. So we're ready to evaluate the definite integral according to the fundamental theorem of calculus. So this is equal to 1/2 times bracket 25 times +5 minus 1/3 times 5 cubed minus same expression now evaluated at -5. So 25 times -5 minus 1/3 times -5 cubed. So we'll simplify now. This is equivalent to 1/2 times 25 times 5 is 125. Excuse me, minus 5 cubed is 125 over 3. And the second group is going to look very similar, but just opposite sign. So -125 plus 125 over 3. And I'll go ahead and put my brackets back so that 1/2 applies to both. So now we just want to reduce and simplify. So I see I can combine 125 and 125 over 3 simply by giving 125 the denominator 3. So I do need to multiply 125 itself by 3. That looks like it's going to be 375. So this is half times 375 over 3 minus 125 over 3. And then again, this same group's going to look very similar. We'll scale it up so we can add the fractions. And again, replace my brackets there so my half distributes correctly. Put the half, and then 375 thirds minus 125 thirds, that's going to give me 250 over 3 plus 250 over 3. Put my parentheses back, and definitely if basically I'm going to double 250 over 3 and then have it, and then what we'll have left is exactly that, 250 over 3. And that completes this volume. So I should put units cubed. There's cubic units. So our first example here, the base is a semicircle. Our cross sections are isosceles right triangles. Let's take a look at an example that has an elliptical base. So for our second example, we're looking at the base of a solid is the region enclosed by an ellipse with a major axis of 8 along the y-axis and a minor axis of 6. So I'm going to start off just by drawing that base. So remember, in an ellipse, the major axis is the longer of the two axes. So if it's a distance of 8, it'll be 4 in each direction from the origin. And then minor axis of 6, so that means direction 3 to the left, 3 to the right, and that gives me my base. We do want to write an equation for that ellipse, so just remembering how to do so, it's going to be x squared over my radius of this minor axis, so that's 3 squared, so it'll be 9, plus y squared over its radius, so that's 4 squared, 16 equals 1. Now I do see that my cross sections are perpendicular to the y-axis and they're semicircles. So I'm going to see that these cross sections look something like so. They're from left to right, and they're semicircles. So what I need to do with my equation is I need to solve it for x. Because my semicircles are defined in terms of y, we'll solve for x. So that's a couple steps here. We're going to subtract y squared over 16. So that's going to give me x squared over 9 equals 1 minus y squared over 16. And then if I multiply both sides by 9, I'll get x squared equals 9 minus 9 over 16 y squared. And then to cancel the square, we'll take the square root, and that'll give me x equals plus or minus square root of 9 minus 9/16 y squared. So that's the equation that I'm going to use to define my cross sections in their area. So we're ready to set up the integration. So it's going to be volume equals, and this is going to be from the lower side to the upper side, since I am perpendicular to the y-axis. So from -4 up to 4. And then I need to give the volume of a semicircle. I'm sorry, an area of a semicircle. So it's going to be half, because it's a semicircle, and then pi r squared. So pi is very easy to include there. R squared is not as immediate. So I've got to think, first of all, that my semicircles are going to be the right side of the ellipse minus the left side of the ellipse. But then I need to divide that by 2 because that's diameter. I need radius. The formula for the area of a circle is half, or I'm sorry, pi r squared, and we're including the half because it's a semicircle. So for my radius, the way that I want to write that is it's going to be half, because I don't need the full distance across, that's diameter, we want radius, times the right side minus the left side. So that's going to be from my equation that we just wrote here. I'll circle it down below. So the right side's the positive version. So that's the square root of 9 minus 9 over 16 y squared minus negative, this is the left side, 9 minus 9 over 16 y squared. So that whole statement, that half times that double radical there, that's my radius. So what I want to do to all of that is square it. My formula again is pi r squared. And we'll include our differential, which again, it's the width of each one of these, dy. So now that we've got it set up, we just want to reduce and simplify. So I'm going to start on the inside of this expression that is for my radius. So I see that this is going to become plus from the double negative. These are identical factors in the square root. So basically it's going to become half times 2 times the square root of 9 minus 9 over 16 y squared. So essentially my half and my 2 are going to cancel out. And so what we'll be left with is this expression in the radical. So we'll start bringing these pieces together. I'm going to let the half pi go on the outside of the integration. So that's going to be half pi outside. And the integration's from -4 to 4. And then definitely I see that my half has canceled with the 2. And then this square root's going to be canceled by the square. So what we're left with is going to be 9 minus 9 over 16 y squared dy. So at that point, what I want to do is actually integrate. So now what we've got is equal to 1/2 pi, and then we treat those as constant coefficients, times 9y, integration of 9, minus 9 over 16, times 1/3 y cubed, and we're integrating from -4 to 4. So as I bring that to my next step, I want to definitely simplify this interior, basically this fraction times a fraction. So it's going to be 1/2 pi times 9. We're going to start inputting according to fundamental theorem of calculus. So 9 times 4 minus, this fraction is going to reduce down. 9 divided by 3 is going to leave me a 3. So it's going to be 3 over 16 times 4 cubed. And need some brackets here. So then we're going to subtract that same expression, but now evaluated at -4. So we're at that stage where we're just simplifying, simplifying, simplifying. So at this point, we've got 1/2 pi times 36. That's 9 times 4. And then for my 3/16 times 4 cubed, 2 of my 4's in the cube are going to be canceling with the 16. So what will be left is 4 to the first power times 3 is 12. So 36 minus 12 minus -36 plus 12. And then 36 minus 12 is going to give me 24 minus negative 24, which is going to be doubled 24, and I'm multiplying by half pi. So that's going to essentially be half times 48, which is back to 24 pi. Units cubed. We're finding volume. And that completes the integration and finds for us the volume of this solid with the base that's an ellipse. Thank you for joining for these two examples of finding volume of solids created by cross sections that are either triangles or semicircles. See you soon.